In today's lecture, we are going to discuss about the blackbody radiation, some of the questions related to the blackbody radiation, Compton and the photoelectric effect, and the De-Broglie wavelength. Some of the questions we are going to discuss. There is a series of questions that I will going to start to discuss about the questions related to the quantum physics and we will start the questions. The first question is the photon of wavelength lambda is incident on the free electron at the rest and is scattered in the backward direction. And simply, uh, you should know first of the basic things about the Compton wavelength, Compton phenomena, and then you will can understood it what they are saying. The functional shift in the wavelength in the term of the Compton wavelength lambda c and of the electron. They are asking the functional shift. We will discuss about the what is functional shift. Before that, the Compton Compton effect is nothing but the change in the wavelength when an photon is uh, strictly collide with inelastic collision with the rest electron of then the scattered photon and have the wavelength less than that of the incident photon. This is given by the simply the Compton phenomena and Compton wavelength. The change in the Compton wavelength is given by this formula lambda dash minus lambda is equal to h by m naught c, where the m naught is rest mass of the electron, c is the speed of light, and then h is the Planck constant. And this is the wavelength of the scattered photon lambda dash, and the lambda is the wavelength of the incident photon, and 1 minus cos theta. It it the change in the wavelength is only depend upon the or depend upon the theta only depend upon the theta is the angle of the scattered photon with the incident photon, and it depend upon the theta only, and it does not depend upon the intensity anything else. And for this they are given in the question that the scattered in the backward direction. It means the theta is when the incident photon is uh, going incident in this direction. The back scattered means the theta is going to 180 degree, and then if the theta is going to 180 degree, then it become 1 minus cos 180 degree cos phi. Cos phi is nothing but minus 1, and minus minus become plus, and the plus 1 and plus 1, and then plus 1 you will get the 2 value, and the shift in the wavelength is nothing but lambda dash minus lambda. And you should know that the Compton wavelength is nothing but h by m naught c. Okay, then this expression becomes 2 lambda c, and change in the wavelength, and they are asking the functional shift. Functional shift is nothing but the ratio of the change in the wavelength divided by the incident wavelength. And then I think the your answer is matching the D, I think. Yes. And the next question is the a black body of the temperature T emits a radiation at the peak wavelength lambda if the temperature of the black body become 4 times. The temperature is going to be 4 times, and they are asking the peak wavelength. For this, we are going to use the Wien's formula. What the formula says that the lambda peak wavelength emitted is equal to lambda max is equal to the B and B's wins constant, some constant is there, and then divided by the temperature of the black body, and then the first expression you will get. This is nothing but they are providing the lambda max is equal to lambda, and from the if we change the temperature to the 40, then the lambda is obviously is going to change, and let's suppose I lambda 2, and then it become b constant remain the same, and then for temperature become 4 times, and then if we divide both the expression, you will get lambda 2 divided by lambda, and 4 the lambda 2 value b by 40, and then lambda value is b by reciprocal. I going to reciprocal it because in the division, and then the t will cancel out and b will cancel out, then the lambda 2, then I think lambda 2 is going to be 1 by 4th of the lambda 2. Okay, then I think the D answer is matching. And the Rydberg, consider a Rydberg hydrogen-like atom in the highly excited state, and they are providing the state number is n is equal to 300, very high, and the wavelength of the radiation come out of these atoms from the transition to the adjacent states lies in the range. Okay, they are asking you the adjacent when the transition happen to the 301, and let's suppose the below is 299. If the transition will happen in these state, the some energy is going to be released in the form of h mu, and from there we will get the lambda. Yes, and simply this change in energy, the energy we are getting h mu is nothing but the Rydberg constant into 1 by f the whole square simply, and minus 1 by initial n square. It means the transition is from the 3, and let's suppose they are asking you the adjacent state. Take any adjacent state, it doesn't matter because they are simply asking you the some range only. And if you put the values ni is equal to put any value, you can put 301 also, you can put 2, put any value because they are seeing the adjacent states, and it is the nf value, sorry, and ni value is 300, the particle is in 300. If you put the all the values, and the Rydberg constant value is 13.6 electron volt, and then you will get the frequency, and then from the frequency you will get the lambda. From the frequency, if you need the lambda is c by mu, and from there if you put the all the values, you will get the radio frequency range. And you can simply say that if you are in the very highly excited state, the n value is very large. Yeah, yeah, then the energy of the adjacent levels are very less, because they are in the very highly excited state. So the energy released, the photon released, energy is, mu value is going to be very less, and so the lambda is going to be very large. So it is in the range of meter. You can directly point out here, and there is no need of the nanometer, picometer, and I think the range is not in there, the pico range, nano range, very small, and it should be in the radio frequency range. For this, for the for that's it, and three questions we have discussed. And that's it. In the further video, we will see the other question. Okay.